All right. And for our third talk, we have Gokul Ravi. He's a 2020 NSF CI Fellow, postdoctoral scholar at the University of Chicago, mentored by Professor Fred Chong. And his research targets quantum computing architectures and systems, primarily focused on themes at the intersection of quantum and classical computing. And he received his PhD in computer architecture from Wisconsin in 2020, where he was advised by Mikko Lapasti.
I'm audible? Okay, great. All right, yeah, thank you, Brandon, for the introduction. So hello, everyone. I'm Gokul Ravi from the University of Chicago, and I'm going to present CAFQA, which is a quantum-inspired a classical initialization algorithm for variational algorithms. So variational algorithms are very useful in the near term of quantum computing because they're fairly robust to noise, but not robust enough right now to do like useful stuff for a lot of algorithms. So this work is very timely in terms of helping variational algorithms do useful stuff. So, and the claim to fame for this work is that in the application of molecular chemistry, which is one of the key applications for variational algorithms, so CAFQA is able to achieve a significantly better initialization than the premier chemistry-based initialization approach, which has been around for nearly 100 years. And CAFQA is able to achieve more than 99% improvement in its in the initialization inaccuracy in the prior work. So, and this work is a collaboration between U Chicago, Super.tech, MIT, Tufts, and Duke. Okay, so I'm going to start with an overview of variational algorithms and CAFQA. So consider this optimization contour, which can be from any classical optimization problem, right? So you have this golden star which you're trying to reach, and you're trying to navigate this from some random initialization point, which is this pink star, and you're using something like gradient descent to navigate this contour. Now, a variational quantum algorithm is essentially the quantum analog of what I just showed. Instead of evaluating each objective function value for this contour on a classical device, you're instead evaluating it on a quantum device, but you're essentially doing the same gradient based approach to find this golden star. Now you can imagine that if the quantum machine was noise free, then traversing this optimization contour doesn't have to be any more challenging than the classical contour I showed earlier. But unfortunately, quantum machines are very noisy, and so this contour becomes much more complicated to navigate, and you have things like these noise-induced local minima, then regions where you don't have any gradients to follow, and so on. So it becomes much more challenging to converge accurately to the target solution. And this is why we need like many approaches to improve upon this. So CAFQA is one such approach to combat this. And the first key insight for CAFQA is that there are actually some points in this quantum space, which are these green dots you see here, which can actually be run efficiently in polynomial time on a classical computer. So now this is really critical. So this entire orange space is filled with quantum points which require a quantum device, except for these green dots, which come from the space known as the Clifford space. And so they can alone be run efficiently on a classical device. And because they can be run on a classical device, they are noise free, which is of course great for this algorithm, because all the other points are going to be affected by noise. So what CAFQA does is that it first searches only through these green dots, this discrete set of points, to find the point which is of the lowest energy among these, right? And it is going to use this point as an initialization for the variational algorithm. And now, because it's a discrete set of points, you need a good algorithm to navigate this, and we find like a Bayesian optimization-based approach is good to do this. Now, once this good initialization point is found, then CAFQA navigates the optimization contour starting from this good initialization point, which means that a lot of the noise which is potentially present in this noisy contour can be avoided, right? And of course, the pink star doesn't have to necessarily be very close to the yellow star, but it's still much better than having a random initialization or some of these state-of-the-art initializations. And as I'll show in some of my results, it's fairly accurate for some very important chemistry problems. Okay, so now I'm going to dive a little bit deeper into how variational algorithms work and why CAFQA is able to do what it does. So as I mentioned earlier, variational algorithms involve navigating through this optimization contour. And this is useful in problems in chemistry, optimization, drug synthesis, finance, and so on. So the idea is that each point in this orange contour is generated using a quantum circuit. And this is a parameterized quantum circuit known as an ansatz. And you can see in this figure that there are all these pink blocks, which are these single qubit gates, which are controlled which can be tuned, and tuning them to different values essentially takes different values on that block sphere, which you see at the top. And this creates different quantum states, which then corresponds to different objective function values in that contour. And a classical optimizer is used to actually fix these gates to different values. And this is what navigates us through that contour. Now, in the context of Kafka, the key point to note is that suppose all of these tunable pink gates, purple gates, can take any value from 0 to 2 pi. Then this creates your general quantum circuit, which requires a quantum device to run it. On the other hand, if these gates take only these discrete set of values, which are multiples of pi by 2, then these correspond to what are known as Clifford gates, and this ends up creating what is known as a Clifford circuit. Now, it is known theoretically from this Gottesman-Cannell theorem that these Clifford circuits can be simulated classically in polynomial time. So what Kafka does is that it only searches through these instances of the circuit, which are made up only of these Clifford gates, that is these multiples of pi by 2, and tries to, among those, find this point which has this minimum energy. Now, as I mentioned, to do this, we use this Bayesian algorithm, Bayesian optimization approach. And I'm going to give a very high-level overview of how this works. So consider that we have this unknown function, which is the one in purple, and you're trying to find the maximum value for this, which is pointed by the arrow, right? And in order to find this maximum value, we are going to use something known as a surrogate model, which is shown by this, the black line over here. Now, we want this black line to map this purple line, so we make queries on this purple line, and we want to make those queries as few as possible, right? So you can see that over the course of few iterations, this black line slowly maps this purple line. And after these 8 iterations, you can see that it has well mapped this purple line. And the key point is that a lot of samples have been taken in the region of interest. And the way this is done is using something called an acquisition function. And this is something like a hyperparameter you tune for your system. So in this work, we use this hypermapper tool from Stanford, which essentially is a parameterizable tool. And we use a surrogate model, which is a random forest-based approach, because this is a discrete set of points that we are trying to navigate. And the acquisition function is something which is called a semi-greedy acquisition function, which means that you can sort of tune it to take more samples in the region of interest and fewer samples to map the entire space. But these things can, of course, be tuned to make it more suitable to your problem. Now I'm going to talk about the benefits of this work in the context of chemistry applications. And I'm going to describe evaluating the potential energy of a molecule. And the potential energy is essentially the energy required to completely break a molecule into its subatomic components. And this is useful in a lot of chemistry problems. So in this graph over here, we are trying to find this dashed line, which is at this minus 7.8 in Hartree, which is a unit of energy. And this energy number is for the lithium hydride molecule at a particular bond length. And of course, we know this value because it's a simple molecule and we can use classical approaches to estimate this energy. But you can imagine that if it's a more complex molecule with more significant quantum properties, then we don't have this dashed line. So we are going to use this VQA approach to try and find this energy value. Now I'm showing 2 VQA approaches here, this blue line and this green line. And both of these are starting at different initialization values, and they are running on a quantum computer in the presence of noise to try to find this energy. So I should note that over here, I'm showing this in noisy quantum simulation, and this is not a quantum device itself. So now you can see that this blue line is using this Hartree-Fock initialization, which is what I mentioned at the beginning to be this chemistry-based approach. And the key idea here is that you can make some approximation to your molecular structure in terms of restricting the spins of your electrons and so on. And this, of course, makes it approximate in terms of the electronic configuration it can navigate, but it makes it a classically tractable problem. So Hartree-Fock is fairly accurate, but it still suffers inaccuracies in some configurations, like you see over here, where you start with an initialization value of around minus 7.6, but it becomes tough to navigate the space due to noise. You see a lot of spikes, and you see that it converges in around 1,000 iterations. On the other hand, the Kafka initialization in this example starts with almost a perfect initialization itself. It's close to minus 7.8. And you can see that not only is the initialization like 100x more accurate, it is also able to converge to the exact answer in like 80 iterations, which is 12x better than the Hartree-Fock based approach. And in fact, even at the point of convergence, though it's less visible in this figure, the Kafka approach is more accurate than the blue line, which is the Hartree-Fock approach. And now we want to use this potential energy, which is for a particular bond length, to actually construct these kind of curves, which are known as a dissociation energy curve. And the idea is that This is the energy which it would take to break bonds as your bond length increases. And this is useful for estimating the rates of chemical reactions and therefore is directly useful for chemistry problems. Now, again, over here, we want to create this orange line, which is the true dissociation energy curve, but we want to construct that using a variational algorithm because this has quantum properties. And so it's tough to do with classical methods for complex molecules. Now, what this is showing in terms of the blue line and the green line is the initialization values for these different approaches, this Hartree-Fock approach and the CAFQA approach. So you can see that the CAFQA line, the green line, is always equal to or better than the Hartree-Fock line, right? And especially at the higher bond lengths, you can see that it is much better than the Hartree-Fock line. And this is not just empirical evidence over here. We know for a fact that for theoretical reasons that the CAFQA line will always be equal to or better. And I'm happy to talk more about that offline. But the key point here is that this Hartree-Fock approach is known to be good at lower bond lengths and near this equilibrium region, but it is known to deviate away from goodness when you go to higher bond lengths. But you can see that the Hartree-Fock approach is, the CAFQA approach is accurate throughout. Now, of course, there is some difference between the green line and the orange line. And this is, of course, expected because this is a problem which does have quantum advantage. And it is this difference between the green line and the orange line that we want to navigate on a quantum device. But clearly, you can see here that using this kind of a classical approach has brought this green line as close to the orange line as possible, which means there's less work for the noisy quantum device to do. Now, of course, this is just one example for this kind of a small molecule, but we also did a lot of evaluation for more complex systems going up to like 34 qubits. And this CAFQA-based initialization achieves more than 99% initialization accuracy across this variety of different problems and different molecular configurations, which means it's a very useful initialization approach. And we observed, similar to what you see in this example, that it is able to recover a lot of the inaccuracy which is present in some of the state-of-the-art approach like this Hartree-Fock approach. And also, finally, I want to note that this Bayesian optimization algorithm, which is a classical algorithm, takes around a few thousand iterations to converge, which, depending on your classical device, can take a few hours of wall clock time. Now, it's worth noting that depending on how much classical computational resource you're ready to throw at your problem, you can even do better than Kafka and even throw some non-Clifford states into your problem and even go closer to the orange line. And that's an interesting area of future research. So to conclude, initialization is critical for variational algorithms to accurately converge, especially on noisy quantum machines. And Kafka initializes VQA by tuning in this Clifford space. And this is a scalable approach and uses Bayesian optimization and achieves significantly higher accuracy compared to the state of the art. And before I conclude, I also want to point out that I also want to note that if you are interested in working on these kind of classical problems for these or classical challenges for quantum problems, we have a workshop at ISCA, which will be a nice place if you want to try, for example, different optimization algorithms to replace or beat the Bayesian optimization I showed here. You can potentially do that, or extend this to multiple other domains, or work on any of the topics which the other authors discussed as well. So with that, I'll stop, and yeah, thank you for your time, and I'm happy to answer questions.